Let's say we have a parabola, y equals x squared, and we wish to find the equation of the tangent line to the curve at a particular point. A parabola, we'll see a better graph on the next slide, looks something like this. Right? And the point 1, 1 might be here, and we'd like the equation of the tangent line that just touches at that point. And moreover, it doesn't just touch, it doesn't intersect the curve, it's tangent to the curve. Meaning when we zoom in on the curve and the line are indistinguishable. But how do we find slope? Normally slope is rise over run, and it still represents that here. We calculate slope by finding the change in the y variable divided by the change in the x variable. Or if we have 2 points on the line, let's call them y2 and y1, x2 and x1, we can calculate the difference in the y coordinates and divide by the difference in the x coordinates. But how do we get the slope when we only have 1 point? The trick, since we only have 1 point to work with, the point of tangency, in this case the point P is labeled here at 1, 1. The trick will be to choose a second point on the graph. Let's call that second point Q. And for now I haven't decided what the x-coordinate of that point will be, but once I decide the x-coordinate, the y-coordinate is determined from the graph, or from the function. Right. The line connecting those 2 points, P and Q, is called a secant line. Right. So the secant line is the light blue line in this picture. How do I find the slope of that line? Well, let's write down the formula. Well, again, it's rise over run, so I'm going to take the difference in the y-coordinates. We'll start with Q. Doesn't matter the order, as long as you're consistent in the numerator and the denominator. We're going to divide by the change in x. So for instance here, if we were to pick x to be 1.5, then the y-coordinate is 2.25. So the slope of the secant line is 2.5. Now that just gives us the slope of the blue line, or the secant line. How are we going to use that to find the slope of the tangent line, in this case the pink line? Well, the idea is to consider what happens as this point Q gets very close to the point P. In calculus we call that a limit. We want to find the limit of the slopes of the secant lines. That is, as Q gets as close as it can to P, without actually touching it, what is the value of the slope that we're approaching? To get a numerical idea how this works, let's look at the next slide. Okay. So if I take x to be 1.5, we saw that the slope on the previous slide was 2.5. If I decrease x closer and closer to 1, so as x approaches 1, I see that the value of the slope is getting closer and closer to 2. Now we don't have to choose x to be bigger than 1. We could also choose x to be smaller than 1. So for instance, if I took the point on the left, if I took Q to be to the left of P, where x is 0, we'd find that the slope is 1. And as I move closer and closer, as x gets closer and closer to 1 without equaling 1, all right, I see that the slope is getting close to 2. So we write the limit as P approaches Q of the slope MPQ is equal to 2. So the slope of the tangent line is the limit of the slopes of the secant lines. Another way to say this is to say as x gets very close to 1, as x gets closer and closer to 1, the value of this slope expression gets closer and closer to 2. Notice here I cannot make x equal to 1. If x equals 1, then I'm dividing by 0. In fact, if x equals 1, I've got 0 on top, 1 squared minus 1, and 0 on the bottom, 1 minus 1, and that expression doesn't make any sense at all. But as x gets very close to 1, the limiting value, or the value that the slope is approaching, is 2. Now the original problem called for us to find the equation of the tangent line. So remember, we are on the graph of the parabola here at the point 1, 1, and we've just discovered that the slope of the tangent line is 2. Now normally when we ask for the slope, for the equation of the line, it's usually customary, though not always, to get the line in slope-intercept form. Right? So m here is the slope that we've just seen, and b is the value of the y-intercept. Okay, of course we can see in our picture here that that's going to be negative. Now it's perhaps easier to start with the point-slope form equation of a line. So here, if we have a point x0 or x0, y0 on the line, so in this case we know 1, 1 is on the line, right? And we found, using the idea of a limit, that the value of the slope for the tangent line is 2. Then we can just plug those things right into our equation in point-slope form. So we have y minus y0, or y0, equals m times x minus x0, or x0. Now if we simplify this, we can easily get the line in slope-intercept form, which is often what you'll see when you look for the answer in the back of the book. So I had to distribute that 2, and I'm going to add 1 to each side. So this minus 1 here, I add 1 to each side to get, or finally, y equals 2x minus 1. So the value of the slope is 2, as we predicted from calculus, from a limit. And the value of the y-intercept is -1, which is consistent with the kind of y-intercept we'd see in our picture here.